Imagine standing outside on a perfectly clear night. The air is cold against your skin. Above you, the sky stretches out in every direction. A vast, black canvas dusted with points of light so ancient that some of them no longer exist. The stars you see with your naked eye burned out millions of years ago. What you're looking at is a ghost, a memory of fire. And yet, somehow, that fact barely scratches the surface of how deeply, profoundly strange the universe actually is. Now ask yourself this: what if the cosmos isn't just strange? What if it's actively, fundamentally disturbing? What if the closer we look, the more we find that the universe operates by rules so bizarre, so incomprehensible, so deeply unsettling, that the most brilliant minds in human history have been left shaking their heads, unable to sleep, questioning everything they thought they knew? Because that is exactly what has happened, and that is exactly what this story is about. We're going to go on a journey together, not through space as it appears in science fiction, with gleaming ships and heroic voyages, but through the real cosmos, the one that exists right now, outside your window, above your head, beneath your feet, inside every atom of your body. And what we are going to find is going to be extraordinary, terrifying, humbling, and absolutely, undeniably real. There are mysteries out there that scientists have been wrestling with for decades. Mysteries that have driven careers, ended careers, sparked revolutions in how we understand reality, and left even the most confident researchers whispering that maybe, just maybe, we understand far less than we think. There are phenomena happening right now, at this very moment, that have no explanation. There are discoveries so startling that when scientists first made them, they assumed they had made a mistake, because the alternative was too strange to believe. And then the data kept coming back, again and again, confirming the impossible. We'll talk about the void in space so empty it seems to violate the laws of physics. We'll talk about a signal so strange it has never been explained. We'll talk about a star that behaves in ways no known natural phenomenon can account for. We'll talk about a substance so abundant it makes up most of the universe, and yet we have never seen it, never touched it, never directly detected it in any way. We'll talk about an energy that is tearing the universe apart at an accelerating rate, and we have absolutely no idea what it is. We'll talk about the possibility, taken seriously by physicists, that reality itself might be a simulation. We'll talk about places where the laws of physics as we know them simply stop working. We'll talk about the deep, quiet possibility, one that terrifies scientists more than almost anything else, that we might be utterly and completely alone. And we'll do all of this not with jargon, not with equations, not with the cold language of textbooks, but with the kind of raw, honest storytelling that these discoveries deserve. Because these are not just scientific puzzles. These are the questions that reach into the deepest part of what it means to be a conscious creature, alive in a universe you didn't ask to exist in, trying to make sense of a reality that may not have been designed to be sensed at all. So take a breath, look up, and let's begin. Let's start at the beginning. Not the beginning of humanity, or even the beginning of Earth, but the beginning of everything. The moment, approximately 13.8 billion years ago, when all the matter, energy, space, and time in the observable universe erupted from a state of almost incomprehensible density and heat in what we call the Big Bang. And already, right here at the very start, we have our first deeply disturbing mystery. Because here's the thing, we don't actually know what caused the Big Bang. We don't know what, if anything, came before it. We don't know whether the word before even has any meaning in that context. We don't know whether the Big Bang was unique, a single, unrepeatable event, or whether it was one of an infinite series of bangs, each one birthing a new universe, like bubbles rising forever through some cosmic ocean we can never see. What we do know is this. Approximately 13.8 billion years ago, everything we can observe emerged from a point smaller than an atom. And that emergence, that first fraction of a second, contained within it every atom in your body, every star you've ever seen, every galaxy we've ever mapped, every thought any human being has ever had. Physicist Sean Carroll, one of the most respected voices in theoretical physics, has spent years grappling with this question. In his work and his writing, he describes the Big Bang not as an origin point but as a boundary, a place where our current physical theories simply stop working. Our equations can take us to within an almost impossibly small fraction of a second after the bang, within a Planck time, which is approximately 10 to the power of negative 43 seconds, a number so small it is essentially meaningless to human intuition, but they cannot take us through that boundary. At the moment of the bang itself, the mathematics breaks down. The equations go to infinity, and when equations go to infinity in physics, that is what scientists call a singularity. And a singularity, in plain language, means we have no idea what is happening here. Ask yourself this: does it unsettle you that the very first moment of all existence is completely hidden from us? That the universe may have had a cause we can never investigate? That before the Big Bang, the words before and where may have had no meaning at all? It should. Because what that means is that we are living inside a story whose first page is written in a language we cannot read. The universe began, and we don't know why. We don't know how. We don't know what, if anything, it emerged from. And we may never know. Not because we haven't tried hard enough, not because we're not smart enough, but because the answer may genuinely lie beyond the boundaries of what is physically possible to know. And that, friends, is where our journey into the disturbing mysteries of the cosmos truly begins. Now let's talk about something that should disturb you on a personal level, because it speaks to the very fabric of what you think of as solid, real, touchable reality. Look at your hand right now. Look at your fingers. They seem solid, don't they? They seem real, physical, tangible. You can feel them. You can move them. They are the most immediate, undeniable evidence you have that there is a physical world outside your mind. Now here is what physics tells us about that hand. It is almost entirely empty space. The atoms that make up your hand, the carbon atoms, the oxygen atoms, the hydrogen atoms, each one of them consists of a nucleus surrounded by a cloud of electrons. The nucleus sits at the center of the atom like a marble sitting in the middle of a football stadium. The electrons orbit somewhere around the edges of the stadium. And between the marble and the edge of the stadium, nothing. Emptiness. The void. If you scaled an atom up to the size of a cathedral, the nucleus would be the size of a grain of rice sitting on the altar. The rest of the cathedral, all of that magnificent, vaulted, cavernous space, would be empty. This is not a metaphor. This is not an oversimplification. This is physics. Your hand is almost entirely empty space. The reason it feels solid is not because it is solid. It is because the electromagnetic forces between the atoms repel each other so strongly that matter cannot pass through matter. What you feel when you touch something is not the thing itself. It is the electric force of repulsion between atoms. You have never touched anything in your life. Not really. Not in the deepest physical sense. Every time you've held someone's hand, every time you've felt the warmth of sunlight on your skin, every time you've pressed your feet against solid ground, you were experiencing the electromagnetic repulsion of atoms separated by a vast, yawning emptiness. Take that in for a moment. Because we're not done. The particles that make up those atoms, the protons, the neutrons, the electrons, what are they exactly? When physicists pushed that question as far as it could go, they found something that is almost more disturbing than the emptiness. They found that fundamental particles don't really behave like little balls or pellets of matter. They behave like waves. Or rather, like something that is neither a wave nor a particle, but something in between, something that doesn't have a definite position until you look at it, something that exists in a kind of blurry probability cloud of all the places it could be until the moment of observation collapses that cloud into a single, definite location. This is the heart of quantum mechanics, and it is genuinely one of the most disturbing things physics has ever uncovered. Not disturbing in the sense of complicated. Disturbing in the sense of it violates everything our intuition tells us about reality. At the quantum level, the universe doesn't seem to be made of things. It seems to be made of possibilities, probabilities, potentials. and those potentials only become definite realities at the moment they interact with something else. Richard Feynman, the Nobel Prize-winning physicist widely regarded as one of the greatest physicists who ever lived, said this about quantum mechanics. If you think you understand quantum mechanics, you don't understand quantum mechanics. He wasn't being modest. He was being honest. Quantum mechanics is the most precisely tested, most experimentally verified theory in the history of physics. Its predictions match experimental results to an accuracy of better than 1 part in a trillion. It underpins every transistor in every computer, every solar panel, every laser, every MRI machine. We use it constantly, every day, in technology that shapes modern life. And yet nobody, not Feynman, not Einstein, not the greatest physicists alive today, truly understands why it works the way it does. Nobody knows why the universe, at its most fundamental level, behaves like this. And here is the question that has haunted physicists for nearly a century. If the position of a particle is not definite until it is observed, then what determines the outcome? What decides which possibility becomes reality? Is it random? Truly random, with no cause, no reason, no deeper mechanism driving it? Or is there a hidden layer of reality beneath quantum mechanics, one that we haven't discovered yet, in which everything is deterministic and causal after all? We don't know. More than a century after quantum mechanics was developed, we genuinely do not know what it means. We know how to use it. We know it works. But what it is telling us about the nature of reality, that is still, terrifyingly, an open question. Let me take you somewhere now. Somewhere specific. Somewhere that, when scientists first looked at it closely, made them feel a cold sensation that is surprisingly rare in the history of science. The sensation of looking at something that should not be there. It's called the Boötes Void. Named after the constellation in whose general direction it lies, the Boötes Void is a region of space roughly 700 million light-years from Earth. And it is one of the largest known voids in the observable universe, a nearly spherical region of space approximately 330 million light-years across. Now, to understand why that matters, you need to understand something about the large-scale structure of the universe. When you zoom out far enough that individual galaxies look like grains of sand, the universe is not uniform. It has structure. It is organized, in the most incredible way, into a vast cosmic web, a network of filaments, long threads of galaxies and dark matter stretching across incomprehensible distances, connected at nodes where massive galaxy clusters sit like enormous cosmic cities at the intersections of highways. Between these filaments and nodes, there are voids, regions of space where matter is relatively sparse. This is normal. This is expected. The universe, on the largest scales, looks like a sponge, or like soap bubbles, dense walls surrounding empty spaces. But the Boötes Void is different. The Boötes Void is not just sparse. It is almost completely empty. When astronomers first surveyed the region in 1981, led by Robert Kirshner and his colleagues at Harvard, they expected to find the usual scattering of galaxies. Even in a void, you'd expect some. Instead, they found almost nothing. A region of space roughly 330 million light-years across containing only about 60 galaxies, when a region that size should contain thousands upon thousands. The original discoverers were so startled by the finding that their first instinct was to assume they had made an error. They went back and checked the data. They found the same result. Kirshner himself reportedly said, "I keep telling people that if the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Let that land for a second. If we lived in the middle of the Boötes Void, the universe would have appeared to our telescopes for most of the 20th century as a single galaxy, our own, floating in an empty cosmos. The universe would have seemed, from that vantage point, utterly alone. The Boötes Void is so vast and so empty that astronomers struggle to explain it using standard cosmological models of how the universe evolved. The current models of cosmic structure formation, which describe how gravity slowly pulled matter together from the near-uniform distribution after the Big Bang, creating the cosmic web we observe, don't easily produce voids this large. For a void the size of Boötes to have formed naturally from the early universe in the time available, the models suggest it would require conditions that strain credibility. Some cosmologists have proposed that the Boötes void might have formed from the merger of smaller voids, that over cosmic time, smaller empty regions expanded and merged into one colossal void. This is technically possible within existing models, though the sheer scale of the Boötes void still makes it unusual. Others have pointed out that we may simply be dealing with a statistical rarity. The universe is enormous, and occasionally, even unlikely arrangements will appear somewhere in its vast expanse. But here's the thought that I want to leave with you, the thought that some theorists have genuinely entertained. What if the Boötes void is the scar of something? What if a vast, incomprehensible cosmic event, a collision of cosmic strings, a remnant of the inflationary epoch, something we haven't thought of yet, left this enormous empty wound in the fabric of the universe? We don't have evidence for that. It's speculation. But the Boötes void is real. It is there. It is empty in a way that is difficult to fully explain. And it is one of the many reminders that the universe does not feel obligated to behave the way our models predict. Now I want to talk about a sound, or rather, the closest thing we have to a sound from the dawn of time. And the way we found it is one of the most remarkable stories in the history of science. It's 1964. Two radio astronomers, Arno Penzias and Robert Wilson, are working at Bell Labs in Holmdel, New Jersey, using a large horn-shaped antenna to study radio waves from the Milky Way. They keep picking up a faint, persistent hiss, a background noise in their equipment that they cannot eliminate. They assume it's interference. They look for sources. They find none. They famously notice that pigeons have been nesting inside the antenna horn, and they spend considerable time cleaning out the nest and what they diplomatically describe as white dielectric material, pigeon droppings, from the interior of the antenna. They shoo the pigeons. They clean the antenna. They rerun their measurements. The hiss is still there. It is coming from every direction in the sky simultaneously. It does not vary with the time of day, or the season, or the direction the antenna is pointed. It is perfectly uniform. It has a temperature, or rather, it corresponds to thermal radiation from a source with a temperature of approximately 2.7 Kelvin, just barely above absolute zero. What Penzias and Wilson had discovered, without intending to and without initially understanding what they were looking at, was the cosmic microwave background radiation, the CMB. It is, in the most literal sense possible, the afterglow of the Big Bang. It is light, electromagnetic radiation that was released approximately 380,000 years after the universe began, when the cosmos had cooled enough for hydrogen atoms to form and the universe became transparent for the first time. Before that moment, the universe was a dense, hot plasma, opaque to light the way the interior of the sun is opaque. When the atoms formed and the fog lifted, light was free to travel, and that light, stretched and cooled by 13.8 billion years of cosmic expansion, is what Penzias and Wilson detected as that mysterious hiss. They won the Nobel Prize in Physics in 1978. The CMB is extraordinary on its own, but here is where it becomes disturbing. When we map the CMB across the entire sky, and we have done this with extraordinary precision with satellites like COBE, WMAP, and most recently the Planck satellite, we see that it is almost perfectly uniform. The temperature variations across the entire sky are tiny, on the order of 1 part in 100,000. The universe, at 380,000 years old, was almost perfectly smooth, almost perfectly the same in every direction. Almost, but not quite. There are tiny fluctuations in the CMB, small variations in temperature that correspond to small variations in density in the early universe. These fluctuations are the seeds of all the structure we see today. The galaxies, the clusters, the filaments, the cosmic web. They are the initial conditions from which everything arose. But when scientists analyzed the CMB data from the Planck satellite, the most precise and comprehensive map of the CMB ever made, they found something that was not expected. something that is, in the language of cosmologists, anomalous. There is a subtle but statistically significant asymmetry in the CMB. One hemisphere of the sky has slightly different properties than the other. There is a region of the CMB, sometimes called the cold spot, a large, anomalously cold region in the constellation Eridanus, that is colder than the surrounding CMB and larger than standard models easily predict. And most troublingly, there appears to be what some researchers have called an axis of evil, a preferred direction in the CMB, an alignment of certain large-scale features that seems to point in a specific direction across the sky. That last phrase, axis of evil, is dramatic, but it's the term that cosmologists themselves have used. And the reason it's alarming is this: our standard cosmological model, the lambda CDM model, which describes the large-scale structure and evolution of the universe, predicts that the universe should be isotropic, the same in all directions, with no preferred axis, no favored direction. The presence of a preferred direction in the CMB, if it is real and not a statistical artifact, would suggest something deeply wrong with our models. It could suggest that the universe has an orientation, that space itself has a direction. It could suggest the influence of something from before the Big Bang, or something beyond the boundaries of our observable universe, imprinting its presence on the fabric of the cosmos. This is not fringe science. The Planck team, the most authoritative group of CMB researchers in the world, has acknowledged these anomalies. They are real. They are in the data. And they do not yet have a satisfactory explanation. Now I want to bring you to one of the most personally haunting stories in all of observational astronomy. A story about a signal. A specific, strange, utterly unexplained signal that was received on August 15, 1977, and has not been satisfactorily explained to this day. It was received by the Big Ear Radio Telescope at Ohio State University, which was part of a program searching for extraterrestrial intelligence, the SETI program. The telescope was scanning the sky, recording data on computer printout sheets. A volunteer astronomer named Jerry Emin was reviewing those printouts several days later when he saw something that stopped him cold. The telescope had recorded a signal that lasted for 72 seconds, the maximum amount of time it could record any given patch of sky as Earth's rotation carried it across the field of view. The signal was strong, incredibly strong, and its characteristics, its frequency, its bandwidth, its intensity, matched almost exactly the theoretical profile of what a signal of extraterrestrial origin should look like. It came from the direction of the constellation Sagittarius. It appeared to originate far beyond our solar system. Jerry Emin circled it on the printout with a red pen and wrote one word in the margin: wow. This is why it is called the WOW signal to this day. In the decades since, astronomers have turned telescopes back to that region of the sky hundreds of times. They have used more powerful telescopes, more sensitive instruments, more sophisticated signal processing. The WOW signal has never been detected again. Not once. Not even a hint of it. In 2016, a team of researchers from the Center of Planetary Science in Florida proposed an explanation. The signal might have been caused by comets. Two comets, 266P/Christensen and P/2008Y2 Gibbs, were in the vicinity of the observed signal, and the researchers argued that outgassing from the comets could have produced hydrogen emissions at the right frequency to be detected by the Big Ear telescope as a strong, anomalous signal. This explanation was controversial. Many SETI researchers rejected it, arguing that the characteristics of the WOW signal, particularly its narrow bandwidth, are inconsistent with comet outgassing, which typically produces much broader signals. The astronomer Seth Shostak, senior astronomer at the SETI Institute, has said that while the comet explanation is possible, it has not been confirmed, and the WOW signal remains the strongest candidate for a signal of potential extraterrestrial origin ever detected. No one has proven it is not extraterrestrial. No one has proven it is. The Big Ear telescope was demolished in 1997 to make way for a golf course. A fact that, if you pause to think about it, is remarkable in its own right. The WOW Signal endures as one of the most tantalizing unanswered questions in astronomy. A single burst of something, from somewhere, that matched the profile of what we'd expect from an alien broadcast, received once, never repeated, never explained, never forgotten. Ask yourself this: if that signal was sent by something out there pointing a transmission in the direction of our solar system, what was it trying to say? And why did it only say it once? Let's talk about dark matter. Because this is one of those stories where the disturbing part isn't the mystery itself, it's the scale of it, the scope of what we don't know. Here's the setup. For most of the 20th century, astronomers were building an increasingly confident picture of the universe's composition. They could see galaxies. They could study their light, measure their motion, calculate their masses. The picture seemed to be coming together. And then astronomers started noticing something wrong. The stars and gas at the outer edges of galaxies are moving too fast. Much too fast. If a galaxy only contained the matter we can see, the stars, the gas, the dust, then the gravitational force holding it together would not be sufficient to keep the outer stars from flying off into space. They're moving at velocities that should, by all rights, cause them to escape the galaxy entirely. And yet they don't. They stay in their orbits, year after year, revolution after revolution, completely ignoring what the math says should happen. The first person to seriously grapple with this problem was the astronomer Fritz Zwicky, who in the 1930s noticed that the galaxies in the Coma cluster were also moving too fast. They were moving fast enough that the visible matter in the cluster shouldn't have enough gravity to hold them together. The cluster should have flown apart long ago, but there it was, intact. Zwicky proposed that there must be dunkel materie, dark matter, some form of invisible mass that was providing the additional gravitational glue to hold things together. For decades, Zwicky's idea was largely ignored. It was not until the 1970s that astronomer Vera Rubin, working with Kent Ford, made the measurements that forced the scientific community to take dark matter seriously. Rubin spent years carefully measuring the rotation curves of galaxies, how fast stars at different distances from the galactic center were orbiting. What she found was unambiguous. Galaxies rotate almost uniformly from center to edge, like a spinning disk, when they should rotate the way our solar system does, with inner planets moving much faster than outer ones. The only way to explain this rotation pattern was if each galaxy was embedded in a vast, invisible halo of matter, dark matter, extending far beyond the visible disk of stars. Rubin's work was meticulous, careful, and reproducible. Other astronomers confirmed her results, in galaxy after galaxy after galaxy. The evidence for dark matter is overwhelming, drawn from multiple independent lines of evidence. Galaxy rotation curves, gravitational lensing observations, the behavior of galaxy clusters, the large-scale structure of the universe, and the precise fluctuations of the cosmic microwave background. Every single one of these independent lines of evidence points to the same conclusion. There is more matter in the universe than we can see. Much more. How much more? This is where it gets truly staggering. Current estimates, based on Planck satellite data and other cosmological measurements, suggest that the ordinary matter we can see and touch and study, the atoms, the molecules, the stars, the planets, everything we've ever directly detected, makes up approximately 5% of the total mass energy content of the universe. 5%. The remaining 95% is composed of things we cannot directly detect. Approximately 27% is dark matter, and approximately 68% is something even stranger that we'll discuss shortly. Think about what that means. Everything you have ever seen, everything science has ever directly studied, every galaxy and every telescope image ever taken. All of that is just 5% of what actually exists. We are like someone who studies the ocean by examining the foam on the waves and calling it comprehensive. The universe is 95% unknown, invisible, and mysterious, and we are only just beginning to understand this. The leading candidates for dark matter are particles called WIMPs, weakly interacting massive particles, hypothetical particles that interact with ordinary matter only through gravity and the weak nuclear force. If WIMPs exist, billions of them should be passing through your body every second. They would be moving through you right now, as you sit and listen, passing through the earth as if it weren't there, almost entirely transparent to matter, like ghosts made of something real. Underground detectors, buried deep in mountains and mines to shield them from cosmic ray interference, have been running for years trying to catch a single direct interaction between a WIMP and an ordinary atom. As of now, they have not succeeded. The WIMPs, if they exist, have refused to reveal themselves. Some physicists have begun to wonder whether dark matter is particles at all. Perhaps it's primordial black holes formed in the early universe, before any stars existed. Perhaps it's axions, another hypothetical particle. Perhaps it's something we haven't thought of yet. Perhaps dark matter will turn out to be the thing that breaks our current understanding of particle physics wide open, the way quantum mechanics broke open Newtonian physics a century ago. And then there's the darkest possibility of all, one that a small but serious group of physicists entertains with increasing frequency. Maybe dark matter doesn't exist. Maybe there is no invisible substance. Maybe our theory of gravity is wrong. Maybe, at the scales of galaxies and clusters, gravity doesn't work quite the way Einstein described it, and what we're interpreting as evidence for missing mass is actually evidence for a modified law of gravity. This alternative framework has a name, Modified Newtonian Dynamics, or MOND, and while it struggles to explain all the observations that dark matter explains elegantly, it is not without its own successes, particularly in predicting galaxy rotation curves. The debate between dark matter particle theories and modified gravity theories is one of the liveliest and most unresolved in contemporary astrophysics. We are 95% ignorant of what the universe is made of. That's the honest truth. And we live our entire lives in the 5%. Now I want to talk about that remaining 68%. Because if dark matter is disturbing, what we're about to discuss is the kind of thing that keeps cosmologists up at night. It's called dark energy, and it is the single most mysterious substance, or force, or property, or whatever it is, in the known universe. To understand dark energy, I need to take you back to 1998. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, were using Type Ia supernovae as standard candles to measure the expansion history of the universe. Type Ia supernovae are exploding stars that reach a predictable peak brightness, which means astronomers can calculate exactly how far away they are by measuring how bright they appear. By measuring the apparent brightness and the redshift, how much the light has been stretched by cosmic expansion of these supernovae at various distances, the teams expected to be able to map out how the expansion of the universe has changed over time. The assumption going in was that gravity should be slowing the expansion down. That's what gravity does. It pulls things together, and over time the mutual gravitational attraction of all the matter in the universe should be putting the brakes on the expansion that began at the Big Bang. What both teams found instead was the complete opposite of what they expected. The universe is not decelerating. The universe is accelerating. The expansion of space is speeding up. Right now, at this moment, galaxies are flying apart from each other faster than they were a billion years ago. Whatever force is driving the expansion isn't weakening, it's winning. It's overpowering gravity on the largest scales of the universe, and it is pushing everything in the cosmos apart at an ever-increasing rate. The discovery was so shocking that both teams spent considerable time checking and rechecking their data, looking for errors, trying to find an alternative explanation. There was none. The results were confirmed independently. The leaders of both teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011 for this discovery. This force driving the acceleration was named dark energy. And here's what we know about it. We know it exists. We know it makes up approximately 68% of the total energy content of the universe. We know it has been causing the universe to accelerate for roughly the last 6 billion years. And beyond that, we know almost nothing. The most common theoretical explanation for dark energy is the cosmological constant, a term that Albert Einstein originally introduced in his general theory of relativity and then famously retracted, calling it his greatest blunder. The cosmological constant can be interpreted as an intrinsic energy density of empty space, a property of the vacuum itself that causes space to expand. Empty space, in this view, is not truly empty. It contains energy, and as the universe expands and the volume of space increases, that vacuum energy increases with it, driving ever faster expansion. But here's the catastrophic problem with this explanation. When physicists try to calculate the expected value of the vacuum energy from first principles, using quantum field theory, which is the theoretical framework we use to describe fundamental particles and forces, they get a number. And that number is roughly 10 to the power of 120 times larger than the observed value of the cosmological constant. That is not a small discrepancy. That is the largest discrepancy between theoretical prediction and experimental observation in the entire history of science. By a factor of 10 to the 120. Physicists call it the worst prediction in physics. Some call it the vacuum catastrophe. Think about what that means. Our best theoretical tools, applied to explaining why the universe is accelerating, produce an answer that is off by a factor of a trillion. And yet the observed acceleration is real. It's happening. So something is wrong, either with our understanding of the vacuum energy, or with our understanding of how it couples to the expansion of space, or with the whole theoretical framework we're using. We don't know which. Some physicists have proposed that dark energy is not constant, that it changes over time, perhaps related to some unknown field that evolves as the universe ages. This hypothetical field is sometimes called quintessence. In 2024, results from the Dark Energy Spectroscopic Instrument, DESI, provided the most detailed three-dimensional map of the universe ever created, covering more than 6 million galaxies and quasars. And the preliminary results suggested, tentatively, that dark energy may not be constant after all, that it may have been stronger in the past and is weakening now, or evolving in some other way. If that is confirmed, it would upend the standard cosmological model and open an entirely new chapter in our understanding of the universe. But the deepest mystery isn't just what dark energy is. It's what it means for the future. Because if the acceleration continues, and current understanding suggests it will, then the long-term fate of the universe is not a contracting death, a big crunch, but something perhaps more haunting, the big freeze. Or something even more extreme. In a universe of accelerating expansion, galaxies move apart faster and faster until they eventually cross the cosmic horizon, the boundary beyond which light can no longer reach us because the universe is expanding too fast. Galaxies that are presently visible will, over billions and trillions of years, slip beyond our horizon. The night sky will darken. One by one, the galaxies will disappear from view. Stars will burn out. Black holes will slowly evaporate through Hawking radiation. The universe will grow colder and emptier and more diffuse, approaching but never quite reaching an ultimate equilibrium, a state of maximum entropy, maximum darkness, minimal energy. This is the big freeze, or heat death. Not a bang, not a crunch, but a slow, infinite, quiet end. And there's an even more disturbing possibility. If dark energy grows over time, if it doesn't just maintain a constant push but increases, then the acceleration could eventually become so extreme that it tears everything apart. Not just galaxies separating from each other, but galaxy clusters shredding, then individual galaxies, then solar systems, then planets, then atoms, in what is called the Big Rip. In this scenario, the expansion of space would grow so violent that it would overwhelm every other force in the universe. Gravity, electromagnetism, the strong nuclear force, and rip apart every structure that exists. Stars would be torn apart. The Earth would be disintegrated. The very atoms in your body would be pulled apart by the accelerating expansion of space in the final moments before the end. The Big Rip, if it happens, is calculated to occur approximately 22 billion years from now, depending on the properties of dark energy. We don't know if it will happen. But we don't know that it won't. We need to talk about black holes. Not because they're mysterious, they are, but we're learning more about them all the time, but because of the specific ways in which they are deeply, philosophically troubling. Ways that go beyond massive gravity and into questions about the nature of information, the nature of time, and whether the laws of physics as we understand them are actually consistent with each other. A black hole forms when a massive star reaches the end of its life and its core collapses catastrophically under its own gravity. When the core is massive enough, roughly above 3 times the mass of the Sun, no force in the universe can stop the collapse. The gravity overcomes even the resistance of neutron degeneracy pressure, and the matter collapses to a point, another singularity, another place where our equations break down, surrounded by a boundary called the event horizon. The event horizon is not a physical surface. You couldn't touch it. You couldn't see it as a distinct line in space. It is a mathematical boundary, defined as the point of no return. The distance from the center at which escape velocity equals the speed of light. Anything, matter, radiation, information, that crosses the event horizon cannot escape. It is, in the most literal physical sense, gone from the observable universe. But here's where it gets philosophically catastrophic. In 1974, Stephen Hawking made one of the most important theoretical discoveries in modern physics. By applying quantum field theory to the space-time geometry around a black hole, he showed that black holes are not truly black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Very slowly, over astronomical timescales, a black hole radiates energy and loses mass. If it doesn't absorb anything new, it will eventually evaporate completely, ending in a final burst of radiation. This is already remarkable. But it creates a problem that has become one of the deepest and most fiercely contested issues in theoretical physics: the black hole information paradox. Here's the problem. In quantum mechanics, information is conserved. This is not just a nice principle, it is a fundamental requirement of quantum theory. If you know the complete quantum state of a system at any given moment, you can, in principle, reconstruct the state at any earlier or later time. Information is never truly destroyed. It might be scrambled, hidden, encrypted, but it exists. This principle is called unitarity, and it is central to the mathematical consistency of quantum mechanics. Now, when matter falls into a black hole, the information about that matter, every detail of its quantum state, appears to be lost. When the black hole eventually evaporates through Hawking radiation, the radiation is thermal. It's the quantum equivalent of random noise, carrying no information about what fell in. If the information is gone, unitarity is violated. Quantum mechanics breaks down. The most successful and precisely verified theory in physics fails, unless the information somehow gets out. But how? The event horizon seems impenetrable. Nothing can escape it by definition. And yet, if information doesn't escape, quantum mechanics is wrong. This is the black hole information paradox, and it has occupied the greatest theoretical physicists of the last 50 years. Hawking himself, for most of his career, believed that information was genuinely destroyed in black holes, that this was a real exception to quantum mechanics. In 2004, at a major scientific conference, he publicly conceded that he had been wrong, that somehow information must escape. But the mechanism remains deeply contested. Physicists have proposed exotic ideas. That information leaks out subtly encoded in the Hawking radiation in a way we don't yet understand, that it's stored in the geometry of spacetime itself, that there are soft hairs, quantum modifications to the event horizon's geometry, a concept advanced by Hawking, Malcolm Perry, and Andrew Strominger shortly before Hawking's death in 2018, that encode information, that the interior of the black hole connects to another region of spacetime through a structure called an Einstein-Rosen bridge or wormhole, and information escapes that way, that at the end of a black hole's evaporation, a Planck scale remnant forms that somehow contains all the information. Most recently, a striking proposal has emerged, the firewall hypothesis, suggested by Ahmed Almhairi, Donald Merolf, Joseph Polchinski, and James Sully in 2012. They argued that if information escapes, the event horizon cannot be the smooth, undramatic boundary that general relativity predicts. Instead, it must be a firewall, a wall of intense radiation at the event horizon that would incinerate anything crossing it. This violates Einstein's equivalence principle, which says that an observer falling into a black hole should notice nothing unusual at the event horizon. Either quantum mechanics is wrong, or general relativity is wrong, or both need to be replaced by something new. There's no clean way out. The information paradox is not a footnote. It is a fundamental collision between the two greatest theories in physics, quantum mechanics and general relativity, and it suggests that at their intersection, something new must emerge. A new theory, a deeper truth, a physics beyond what we currently know. Speaking of things that fall in, let me tell you about something you may have heard of, but perhaps not in quite this context: the sound that a black hole makes. In 2003, NASA's Chandra X-ray Observatory was studying the Perseus galaxy cluster, a massive grouping of galaxies about 250 million light-years away, when scientists noticed something extraordinary in the data: ripples in the hot gas permeating the cluster, pressure waves that corresponded to sound waves propagating through the medium. Sound, in an extremely exotic sense, in the vast, tenuous gas of a galaxy cluster. In 2022, NASA converted those pressure waves into audible sound, transposing them into the range of human hearing, and released the audio. The sound is haunting. There is no other word for it. It is deep, resonant, alien. Not the cheerful music of science education videos, but something genuinely eerie, like a vast organ playing notes in the darkness beneath any frequency you've ever heard in a concert hall. The actual frequency of the waves is B-flat, but 57 octaves below middle C, a note so deep it vibrates at a period of 10 million years per cycle. We are talking about sound waves that take millions of years to complete a single oscillation. The largest musical instrument in the known universe is a galaxy cluster, and it is playing a note that no living thing will ever hear in real time. This is not the disturbing part. The disturbing part is what drives it. The sound is being generated by the supermassive black hole at the center of the Perseus cluster, a black hole with a mass of hundreds of millions of solar masses, sitting in the center of the cluster like a cosmic engine, firing jets of energy into the surrounding gas and generating pressure waves that propagate outward, heating the gas and preventing it from cooling and forming new stars. The black hole is, in a sense, singing. It is singing the death of the stars that might have formed in the gas it is heating. It is singing in a key that no human ear can perceive, at a tempo that no human mind can fully comprehend, in a medium so vast and so inhuman that the word space seems too small a container. Let me shift gears now, from the very large to the very edge of what physics knows. Because we've been dancing around something that needs to be addressed directly. Something that, when you sit with it long enough, becomes genuinely difficult to dismiss. What is space? Not outer space, but space itself. The emptiness. The void between things. We tend to think of space as a backdrop, a neutral, empty container in which matter sits and events occur. But this is not what physics tells us. Physics tells us something far stranger. According to general relativity, space is not passive. Space is dynamic. Space has geometry, and that geometry, the curvature of space, is what we experience as gravity. When Einstein replaced Newton's idea of gravity as a force acting between masses with the idea of masses curving the geometry of space-time, he was saying something profound. There is no such thing as empty space in the old sense. Space is a thing. It has properties. It can bend. It can ripple. It can expand. It can tear. And it does all of these things. We have detected the ripples, gravitational waves, directly. In 2015, the LIGO detector in the United States registered the first direct detection of gravitational waves, produced by the merger of two black holes approximately 1.3 billion light-years away. The ripple that traveled from that merger to Earth distorted the local fabric of spacetime by an amount smaller than 1,000th the diameter of a proton. The scientists detected it. They did the equivalent of measuring a distance equal to the width of a human hair, spread across the entire Milky Way galaxy, to a precision of 1/100th of that hair's width. The technology involved is almost as staggering as the discovery itself. But what are gravitational waves, really? They are distortions in the geometry of spacetime, ripples in the fabric of reality itself, propagating outward from catastrophic cosmic events at the speed of light. When a gravitational wave passes through you, space literally stretches in one direction and compresses in the perpendicular direction. Not the objects in space, space itself. The distances between points stretch and shrink. This is happening to you constantly, from every direction, caused by gravitational waves generated by merging black holes and neutron stars across the universe. The effect is so tiny that you will never feel it. But it is real. Space is dynamic. Space is alive, in a sense, trembling with the echoes of catastrophic events. And now quantum mechanics enters the picture again, and things get even stranger. According to quantum field theory, the vacuum, empty space, is not empty. It is seething with activity. Virtual particles, pairs of particle and antiparticle, are constantly popping into existence and annihilating each other, borrowing energy from the vacuum for the briefest possible moment before returning it. This is called quantum vacuum fluctuation, and it is experimentally verified. The Casimir effect, a tiny but measurable force that arises between two closely spaced metal plates due to the suppression of quantum vacuum fluctuations in the space between them, was predicted theoretically and confirmed experimentally in 1997. Empty space between those plates is slightly different from empty space outside them, because some vacuum fluctuations are suppressed. The plates feel a force. Emptiness has structure. Vacuum has energy. So what is space? It is not nothing. It is not passive. It is curved by mass. It ripples under catastrophic events. It seethes with virtual particles. It possesses an intrinsic energy density. And it is, according to some theoretical frameworks, not truly continuous but rather composed of discrete units at the Planck scale. The smallest meaningful unit of length, approximately 1.6 times 10 superscript 3 meters, in which case the apparent smoothness of space is itself an illusion, a macroscopic average of a deeply grainy quantum reality. We walk through space every day. We take it utterly for granted. We have no idea what it fundamentally is. There is a star in the constellation Cygnus, about 1,500 light-years from Earth, called KIC 846-2852. Astronomers and the public came to know it by a different name. Tabby's star, named after the astronomer Tabitha Boyajian, who led the initial scientific paper describing its strange behavior. And the story of Tabby's star is one of the most captivating, baffling, and still unresolved puzzles in contemporary astronomy. The story begins with the Kepler Space Telescope, which was designed to search for exoplanets, planets orbiting other stars, by detecting the tiny periodic dips in a star's brightness that occur when a planet passes in front of it, blocking a small fraction of the star's light. Kepler was extraordinarily sensitive. Over its years of operation, it detected thousands of exoplanet candidates. Most of the brightness variations it recorded were small, regular, and easy to explain. Then there was Tabby's star. KIC 846-2852 showed brightness variations that were none of those things. Between 2009 and 2013, the star's light dimmed by up to 22%, an enormous amount. A Jupiter-sized planet transiting a sun-like star would dim its light by about 1%. 22% of dimming requires an object with a cross-section almost as large as the star itself. And the dimming was not periodic or regular. It happened at irregular intervals, with dips of varying depth and duration that followed no clear pattern. Sometimes the star dimmed by 22%, sometimes by smaller amounts. The shape of the brightness dips was also irregular, sometimes symmetrical, sometimes not, sometimes showing multiple overlapping dips. When Boyajian and her team published their paper describing the observations in 2015, they went through a thorough list of possible natural explanations and found that none of them fit perfectly. A swarm of comets was the leading natural hypothesis. Perhaps a family of comets had broken apart and was passing in front of the star, their dust and debris causing the irregular dimming. This remains the most widely accepted natural explanation to date. But there was something else. Something that another astronomer, Jason Wright of Penn State University, pointed out when he became aware of the observations. Wright noted that Tabby's star's behavior was consistent with what astronomers might theoretically expect if a highly advanced technological civilization were constructing massive structures around their star. Perhaps an incomplete Dyson swarm, a collection of enormous solar collectors designed to harvest the star's energy. This hypothetical megastructure, first proposed by physicist Freeman Dyson in 1960, would need to be enormous, potentially dwarfing any planet, and its irregular, partially constructed state could explain the irregular, asymmetric dimming patterns. Wright and Boyajian were careful to emphasize that this was not their preferred explanation. It was a last resort after natural explanations. But the alien megastructure hypothesis set the internet on fire, and funding poured in for additional observations. What followed was a years-long, intensive observation campaign. Researchers used radio telescopes to search for signals from the direction of Tabby's star. They found none. They used optical wavelength measurements to study the color of the light being blocked during dimming events. And here the results were telling. During the dips, the star dims differently at different wavelengths. Specifically, it dims more at shorter wavelengths than at longer ones, a wavelength-dependent dimming that is the signature of fine dust particles scattering light. This is what the comet debris hypothesis predicts. Cometary dust would show exactly this kind of wavelength-dependent obscuration. A solid megastructure would block all wavelengths equally. The 2018 paper by Boyajian and colleagues, based on this multi-wavelength analysis, concluded that circumstellar dust orbiting the star, was the most likely explanation for the dimming events. Most scientists accepted this as the leading explanation. But the mysteries of Tabby's star aren't entirely resolved. The origin of the dust is still debated. The source of the long-term secular dimming of the star over longer periods, reported by several studies examining century-old photographic plates, remains puzzling. And the precise mechanism producing the complex, irregular structure of the dips is not fully understood. Tabby's star is a reminder that the universe is full of things that we look at and think, I have never seen anything like that before. Usually there's a natural explanation. But occasionally the explanation takes years to piece together. And occasionally, just occasionally, you wonder. I want to talk about something called the Fermi paradox, because it is one of the most unsettling logical puzzles in the history of scientific thought, and because it relates directly to that wondering we were just doing. In the summer of 1950, the great physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned, as it sometimes does among physicists, to the topic of flying saucers, which were very much in the public discussion at the time. The conversation eventually turned to the general topic of whether extraterrestrial intelligence existed. And Fermi, known for his brilliant rapid-fire back-of-the-envelope calculations, paused and then asked, in a way that seemed to crystallize something everyone had been dancing around, where is everybody? It sounds like a simple question. It is not, because when you do the math, it becomes very, very troubling. The Milky Way galaxy is approximately 100,000 light-years across and contains an estimated 200 to 400 billion stars. Our galaxy is roughly 13 billion years old. Of those hundreds of billions of stars, a very large fraction, current estimates suggest perhaps a quarter to half, have planets in their habitable zones, the range of distances where liquid water could exist on a planet's surface. Given the extraordinary ubiquity of the chemistry of life, carbon, hydrogen, oxygen, nitrogen, the building blocks of organic molecules found throughout the galaxy, and given the incredible resilience and adaptability of life as we know it on Earth, It seems reasonable to expect that life has arisen on some portion of those billions of potentially habitable planets. And here's the key point. Life on Earth took about 4 billion years to produce us, a technological civilization. Our galaxy is 13 billion years old. There are stars in the Milky Way that formed billions of years before our Sun. If any of those stars had Earth-like planets, and if life arose on them at a similar pace, civilizations could have existed in our galaxy billions of years before us. A civilization with a billion-year head start on technology, even assuming it only achieved moderately advanced space travel, could plausibly have colonized the entire galaxy in what, on cosmic timescales, is a brief period. Models suggest that even at a small fraction of the speed of light, a colonization wave spreading through the galaxy would take perhaps a few million years. Against the backdrop of billions of years of galactic history, that is nothing. And yet, we look up, we listen. We have been scanning the sky with radio telescopes for decades, and we find nothing. No signals, no megastructures, no self-replicating von Neumann probes, the kind of autonomous robotic explorers that any sufficiently advanced civilization might plausibly send to every star in the galaxy. No evidence of resource extraction on planetary or stellar scales. The galaxy is silent. The cosmos appears empty of other minds. Where is everybody? This is the Fermi paradox. And the proposed solutions to it range from the reassuring to the deeply, profoundly terrifying. Let me walk you through some of them. One possibility is that we are first. Perhaps the emergence of complex, intelligent, technological life is so rare, requiring such a specific sequence of biological, chemical, geological, astronomical, and purely lucky events that it has happened only once in the observable universe. This is the conclusion suggested by Peter Ward and Joe Kirschvink in what they call the rare Earth hypothesis. The idea that Earth is not merely one habitable planet among billions, but an extraordinarily improbable product of a chain of coincidences that may have occurred only here. If this is true, then we are utterly alone. The silence of the cosmos is not a mystery. It's the sound of an empty universe containing exactly one civilization. Is that reassuring? In one sense, yes. We are special. In another sense, think about it. If we are first, then the universe has spent 13.8 billion years producing stars and planets in chemistry and biology, and the only outcome of all of that vast cosmic process capable of looking back and asking, why? Is us, right now. In this brief flicker of time before either we go extinct or transform into something unrecognizable. If we fail, if we destroy ourselves before we spread life and consciousness into the galaxy, then the universe goes on. Stars burn, galaxies merge, eons pass, and perhaps nothing ever looks up and wonders again. Another possibility. They were there, but something got them. Something that we have not yet encountered. Something that every civilization reaches in its development and does not survive. This is called the Great Filter. The idea was proposed by economist Robin Hanson in 1998, and it goes like this. There must be some step in the development of interstellar civilizations that almost nothing gets through. A filter that eliminates virtually every candidate before it can spread to the stars. Either the filter is behind us, some step in the development of life, or intelligence, or civilization that was nearly impossible and that we somehow passed, or the filter is ahead of us. And if the filter is ahead of us, we have not yet encountered whatever destroys civilizations, and we will. What could the Great Filter be? Perhaps it's the transition from simple prokaryotic cells to complex eukaryotic cells, a transition that took roughly 2 billion years on Earth and seems to require an improbable symbiosis event. Perhaps it's the development of multicellular life, or of intelligence, or of technology. Perhaps these transitions are so unlikely that almost no civilization makes it through. Or perhaps the filter is something ahead. Nuclear war, ecological collapse, the development of artificial intelligence that destroys its creators, a biological catastrophe, the release of a technology too dangerous to contain. Perhaps every civilization, when it reaches a certain level of technological capability, destroys itself. And what we see in the silence of the cosmos is not the absence of intelligence, but the graveyard of civilizations, scattered across the galaxy's history, each one burning briefly and then going dark. Astronomer Frank Drake formulated what became known as the Drake equation in 1961, a formula designed to estimate the number of communicating civilizations in the Milky Way by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets with life, the fraction of life-bearing planets with intelligent life, the fraction of those that develop technology, and the average longevity of technological civilizations. The equation is not a solution. It's a framework for thinking about the variables. And the most important and most uncertain variable is that last one: longevity. How long does a technological civilization last? If civilizations typically last 1 million years, there could be millions of them in the galaxy. If they typically last 1,000 years, about where we are now, there might be very few or one or none. We have been a technological civilization capable of sending radio signals into space for less than 100 years. Whether we will be a civilization at all in another 100 years remains an open question. There's another solution to the Fermi paradox that I find, personally, among the most unsettling. It's called the dark forest theory, articulated memorably in Liu Cixin's science fiction, but grounded in genuine game-theoretic logic. The idea goes like this: any civilization in the universe, when it considers the possibility of other civilizations, faces a fundamental uncertainty. It cannot know whether another civilization is friendly or hostile. It cannot know whether another civilization's values align with its own. And given the existential stakes, the possibility that a hostile civilization, upon detecting you, might destroy you before you can defend yourself, the rational strategy for any civilization might be to remain silent, and to destroy any other civilization it detects, before being detected itself. In this model, the universe is a dark forest, in which every hunter moves in silence, bow drawn, because every other presence in the forest is a potential existential threat. If the dark forest theory is correct, then the silence of the cosmos is not evidence of an empty universe but of a full one, full of civilizations hiding in the dark, not sending signals, not building obvious megastructures, not announcing themselves in any detectable way, watching quietly and lethally for any who do. In this model, our radio transmissions and our active SETI efforts, our deliberate broadcasts aimed at other stars, are not hopeful greetings. They are the howl of prey in a silent forest. I want to be very clear. This is a theory. It is a speculative framework. We have no evidence for it, but it is logically coherent, and it is taken seriously enough by some scientists and thinkers that there is an ongoing debate within the SETI community about whether we should be actively broadcasting our presence to the cosmos. Stephen Hawking himself, in a 2010 documentary series, said, "I imagine they might exist in massive ships, having used up all the resources from their home planet. Such advanced aliens would perhaps become nomads, looking to conquer and colonize whatever planets they can reach. If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans." Hawking advised caution. He was not certain, but he was cautious. Let me take a moment here and ask you to sit with a question. I want you to genuinely think about it, not just pass over it. If you had the ability right now to send a single message to every star in the Milky Way, to broadcast simultaneously to every potentially inhabited world in our galaxy, would you do it? Knowing that we don't know who might receive it, knowing that we don't know what might respond, knowing that if something were to respond, we would not know for decades or centuries whether the response was benign. Would you announce our existence? Would you say, "We are here"? Sit with that, because that is not just a thought experiment. That is a real policy question that real astronomers and real governments have debated, and the world does not have a consensus answer. Now I want to tell you about a discovery that, in my view, does not get nearly enough attention. A discovery that should be in every conversation about the disturbing mysteries of the cosmos, because it challenges something we think we know about the universe at the most fundamental level. It's called the Hubble tension, and it is a crisis. An actual crisis in cosmology. The Hubble constant, named after Edwin Hubble, who first measured the expansion of the universe in the 1920s, is the number that describes how fast the universe is currently expanding. It's expressed in units of kilometers per second per megaparsec. How many kilometers per second faster a galaxy recedes from us for every megaparsec of additional distance? The value of the Hubble constant is one of the most important numbers in cosmology. And for the past decade, as measurements have become more and more precise, two independently derived values of the Hubble constant have been stubbornly, persistently, and now undeniably different from each other. On one side, measurements based on the cosmic microwave background, particularly the exquisitely precise Planck satellite data. These measurements, based on the properties of the early universe and evolved forward using the standard cosmological model, give a Hubble constant of approximately 67 to 68 kilometers per second per megaparsec. On the other side, measurements based on the local universe, distance measurements using Cepheid variable stars and type Ia supernovae as distance indicators, calibrated by nearby objects whose distances we can measure very precisely. These measurements, led by astronomer Adam Rees and the H0 Likau collaboration, among others, consistently give a value of approximately 73 to 74 kilometers per second per megaparsec. The James Webb Space Telescope, launched in 2021, was hoped to resolve the discrepancy by providing more precise measurements, but the JWST data has, in 2023 and 2024, confirmed the higher local measurement, deepening rather than resolving the tension. The discrepancy between 67 to 68 and 73 to 74 sounds small. It is not small. The statistical significance of the discrepancy has now grown to approximately 5 sigma, the threshold conventionally used in physics to claim a discovery. A 5 sigma discrepancy between two carefully and independently derived measurements of the same quantity means that the probability of the difference being due to random error alone is roughly 1 in 3.5 million. This is not a measurement problem. Something is genuinely, physically wrong. Either one of the measurement methods has an unidentified systematic error, something wrong with the calibration chain or the theoretical model, or the standard cosmological model is itself wrong. The universe may be expanding faster than our best theory of its evolution predicts. And if that's the case, something is missing from the model. Something new. An unknown physics. Some proposed solutions include new light particles, a fourth neutrino species, or sterile neutrinos, interacting weakly with the early universe plasma and modifying the expansion rate at that time. Others involve early dark energy, a dark energy component that was significant in the early universe but decayed away. Others invoke modifications to the theory of gravity. None of these proposals has achieved consensus. None has been confirmed. The Hubble tension sits there, in the data, 5 standard deviations strong, daring the field to explain it. Wendy Friedman, one of the world's leading experts on the cosmic distance ladder, gave a talk in 2021 in which she said, and I'm paraphrasing, that the Hubble tension may be pointing to new physics we haven't thought of yet. Adam Rees has been more blunt, saying in interviews that if the tension is confirmed, as it increasingly seems to be, the standard cosmological model will need to be revised. This is the cosmos's way of telling us that the story we're telling about it is incomplete. There is a phenomenon in quantum mechanics that Einstein called spooky action at a distance, and which is now one of the most experimentally verified facts in physics, and which is deeply, genuinely strange no matter how many times you try to get used to it. It's called quantum entanglement. Here's the setup. Two particles interact in such a way that they form a single, entangled quantum system. Once they've interacted, you can separate them by any distance, across the room, across the country, across the universe, and they will remain entangled. The quantum state of each particle is linked to the quantum state of the other. When you measure one particle, when you determine some property of it, like its spin, the corresponding property of the other particle is instantly determined. not after a delay for light to travel between them. Instantly, at the moment you measure particle A, particle B, regardless of how far away it is, snaps into the corresponding definite state. Einstein was deeply bothered by this. He insisted that it must be an illusion, that the particles must carry hidden information about their states from the moment they separated, like pre-written instructions that get revealed upon measurement. He called this a hidden variables theory. He collaborated on a famous paper, the EPR paper for Einstein-Podolsky-Rosen, published in 1935, arguing that quantum mechanics as formulated was incomplete. In 1964, physicist John Bell devised a mathematical test, Bell's inequality, that could distinguish between quantum mechanics and any hidden variables theory. If hidden variables were responsible for the correlations between entangled particles, the correlations would obey certain statistical limits, Bell's inequality. If quantum mechanics was right and the correlations were genuinely non-local, genuinely instantaneous, the correlations would violate Bell's inequality. Experiments have been performed, beginning with Alan Aspect's landmark experiments in the early 1980s and continuing with increasingly sophisticated and loophole-free tests through the 2010s, culminating in the Big Bell test of 2016 and the award of the Nobel Prize in Physics in 2022 to Aspect, John Clauser, and Anton Zeilinger precisely for their experimental tests of Bell's inequalities. The results are definitive. Bell's inequality is violated. Hidden variables theories of the classical type Einstein envisioned are ruled out. Quantum entanglement is real. The correlations between entangled particles are genuinely non-local. But here's the careful distinction that needs to be made, and it's one that's often lost in popular accounts. Quantum entanglement, while it implies non-local correlations, cannot be used to transmit information faster than light. When you measure particle A, the result is random. You don't get to choose what outcome you get. When your partner measures particle B, they also get a random result. Only when you compare notes, which requires a classical, light-speed limited communication channel, do you discover that the results are correlated. You can't exploit the correlation to send a message, because neither you nor your partner controls the individual outcomes. But here's what remains deeply unsettling. The correlations are real, and they are instantaneous, and they involve particles separated by arbitrarily large distances. There is a genuine, non-classical connection between entangled particles, a connection that doesn't care about distance, doesn't diminish with separation, and cannot be explained by any local mechanism. The universe, at the quantum level, is non-local. Reality at its most fundamental is connected in ways that violate our intuitions about space and separation. What does that mean for our picture of reality? We don't fully know. But some theoretical physicists, most notably Juan Meldacena and Leonard Susskind, in work connecting quantum entanglement to the geometry of spacetime through the ER equals EPR conjecture, have proposed that entanglement and the connectivity of spacetime might be deeply related. That what we call spacetime geometry, the fabric of reality, might emerge from quantum entanglement. That the geometry of the universe, at its deepest level, might be woven from quantum connections between its parts. This is speculative. It is beautiful. And if it is true, it means that the structure of space itself, the void you look up at on a clear night, is stitched together by something quantum. By something that, in a sense, makes the universe one connected whole rather than a collection of isolated parts. Now let me talk about something that sounds like science fiction but is taken seriously by some of the most distinguished physicists alive. I want to talk about the possibility that the universe we live in is not fundamental, that it is, in some sense, a simulation. Or more precisely, that it is a mathematical structure or an information processing system, whose relationship to any deeper reality may be profoundly different from what we intuitively assume. The idea that physical reality might be fundamentally informational has a long history in physics. John Wheeler, one of the 20th century's greatest theoretical physicists, the man who coined the term black hole, spent the last decades of his career developing what he called the id from bit hypothesis. The idea that every element of physical reality, every derives its existence from information, from bits. That at the deepest level, the universe is made not of matter or energy but of information, of answers to yes/no questions. Wheeler was not a fringe thinker. He was the mentor of Feynman and Everett, two of the 20th century's most important physicists. And he took this idea seriously. In 1999, physicist Max Tegmark of MIT went further, proposing what he calls the mathematical universe hypothesis. The idea that our universe is not merely described by mathematics, but is a mathematical structure. In his view, every logically consistent mathematical structure exists as a physical reality somewhere. And what we experience as our universe is simply the mathematical structure we happen to inhabit. This framework, which Tegmark laid out in detail in his 2014 book, Our Mathematical Universe, has been controversial but taken seriously in foundational physics circles. But the idea that really caught the public imagination is the simulation hypothesis, articulated most influentially by philosopher Nick Bostrom of Oxford University in his 2003 paper, Are You Living in a Computer Simulation? Bostrom's argument is subtle and logical, not mystical. He points out that if advanced civilizations eventually develop the ability to run detailed simulations of minds and conscious experiences, something that seems plausible given the trajectory of computing technology, then the number of simulated minds would vastly outnumber the number of base reality minds. And if that's the case, any randomly selected mind, including yours, is statistically far more likely to be a simulated mind than a base reality mind. This is a probabilistic argument, not a physical one. It doesn't prove we're in a simulation. But it does argue that if we're not, it's probably because one of three things is true. Civilizations tend to go extinct before they can build such simulations. Civilizations that can build such simulations choose not to. Or we are in a base reality simulation and the reasoning above somehow fails. Each of these three options is interesting in its own right. But Bostrom's point is that at least one of them must be true. Now, here's where it gets interesting from a physics perspective. Are there physical tests of the simulation hypothesis? Are there signatures, detectable in principle, that would distinguish a simulated universe from a base reality universe? Some physicists have said yes. In 2012, theoretical physicists at the University of Bonn, led by Silas Bean, published a paper examining what signatures might appear in a simulated universe if the simulation were being run on a discrete lattice, a grid, rather than on continuous space. They found that cosmic ray particles at very high energies, the highest energy particles we detect arriving from space, might show a characteristic cutoff and directional bias if they were bumping up against the limits of a discrete computational lattice underlying space. Intriguingly, there does exist a measured cutoff in high-energy cosmic rays called the GZK limit, though this has an established astrophysical explanation. The paper was speculative and did not claim to prove anything, but it illustrated that the simulation hypothesis is not, in principle, entirely untestable. Other physicists point to the mathematical precision of the universe's physical laws, the fact that the laws of physics can be written in elegant mathematical form, and that this mathematics works with extraordinary precision across every scale we've examined, as suggestive that reality might have a computational underpinning. Neil deGrasse Tyson famously said, at a public symposium, that he believes the simulation hypothesis may be true, giving it odds slightly above 50%. Elon Musk has made similar statements publicly, though his opinion is not that of a physicist and should be weighted accordingly. There are serious objections. The philosopher David Chalmers has explored the simulation hypothesis extensively in his book Reality Plus, and argues that even if we are in a simulation, this doesn't make reality less real. The simulated objects and experiences are still real, just in a different sense. Other philosophers and physicists argue that the concept is unfalsifiable in practice, and therefore doesn't qualify as a scientific hypothesis in the traditional sense. I am not telling you we live in a simulation. I am telling you that some of the smartest people alive take the question seriously. I am telling you that the question has been formalized in rigorous philosophical and physical terms. And I am telling you that the question touches something deep. If everything you have ever experienced, every love, every grief, every moment of beauty or terror, is occurring within a computational process running on some external substrate. What does that mean for you? What does that mean for consciousness? What does that mean for the universe's claim to be real? Let me bring you to the edge of the universe. Not the edge we can reach, but the edge of what we can see. The boundary of the observable universe. And let me tell you what lies there, and what might lie beyond. The observable universe is a sphere, approximately 93 billion light-years in diameter, centered on Earth. But this is not the universe. This is only the region of the universe from which light has had time to reach us since the Big Bang. The light from objects farther away hasn't reached us yet, not because the universe is too small, but because there hasn't been enough time. But those objects exist. The universe extends beyond our cosmic horizon, almost certainly, and possibly infinitely. How large is the universe beyond the observable part? We genuinely don't know. It could be large but finite. It could be infinite. Current measurements suggest that the universe is geometrically flat, or very close to flat, at the limits of our detection. A geometrically flat, infinite universe would extend forever in all directions, containing infinitely many stars, galaxies, and perhaps infinitely many copies of every possible configuration of matter, including, the mathematics suggests, infinitely many versions of you, your planet, your galaxy, arranged in every possible way. This is not science fiction. This is the logical implication of an infinite, homogeneous universe combined with quantum mechanics. In an infinite universe, every possible arrangement of matter that is physically permissible will be realized somewhere. And not just once, but infinitely many times. If the universe is infinite, there are infinitely many people right now, in distant regions beyond our horizon, living lives identical to yours up to this moment, and infinitely many living lives that differ from yours in every possible way. Cosmologist Max Tegmark has formalized this notion, calling it the Level 1 multiverse, the most basic level of multiverse that follows from a straightforward reading of standard cosmology and quantum mechanics, without any exotic additions. It requires only that the universe be spatially infinite and homogeneous on the largest scales, both of which are reasonable assumptions given current data. But there's a Level 2 multiverse, the one suggested by inflationary cosmology. Inflation is the theoretical framework that postulates a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang. An expansion so fast that a region of space far smaller than an atom inflated to a size larger than the current observable universe in a fraction of a second. Inflation was proposed to explain several observed features of the universe: its large-scale flatness, its uniformity, the pattern of fluctuations in the CMB, and it is widely accepted as the best current explanation for these features. But inflation, in most theoretical implementations, doesn't stop cleanly. Once inflation starts in a region of space, it keeps going in most of that space, while occasionally stopping in small patches, each patch becoming a bubble universe with its own physical properties. In the framework called eternal inflation, this process goes on forever. The universe is an eternally inflating sea of space-time, dotted with bubble universes like ours, each one with potentially different physical laws, different values of fundamental constants, different numbers of dimensions. We are one bubble among an endless ocean of bubbles, most of which we can never access, never see, never communicate with. If this is true, and many physicists find eternal inflation theoretically compelling, though it remains unproven and perhaps unprovable, then the properties of our universe that we've been studying, the laws of physics, the values of fundamental constants, might not be inevitable. They might be accidents of which bubble universe we happen to find ourselves in. The constants of physics might not be derivable from a deeper principle. They might just be what they are in our particular bubble, among an infinite variety of other values in other bubbles. And this has a profoundly uncomfortable philosophical implication. If the constants of physics are just accidents of our bubble, then we can never truly understand why the universe is the way it is. We can only describe it. The explanatory project of physics, the goal of understanding why the laws are what they are, might be, in this framework, ultimately unanswerable. Now I want to tell you about one of the most profound mysteries in all of science. One that is not about black holes or dark matter or the Big Bang, but about you. About the fact that you're listening to this or reading this, and there is something it's like to be you doing that. About the hard problem of consciousness. The hard problem of consciousness was named by philosopher David Chalmers in 1995, and it is this: why does physical processing in the brain give rise to subjective experience? Why is there something it's like to be a conscious being? Not how the brain processes information, that's the easy problem. And while it's not actually easy, it's the kind of problem we know how to approach. More neuroscience, better brain imaging, deeper understanding of neural circuits. The hard problem is different. Even if we had a complete, perfect map of every neuron, every connection, every firing pattern in the brain, even if we could predict exactly how the brain would respond to any input, we would still face the question: why does any of this give rise to experience? Why isn't it all just information processing in the dark, with no inner life, no feeling, no perspective? This is not a new question. Philosophers have grappled with it for centuries under various names: the mind-body problem, the explanatory gap. But in the context of neuroscience and physics, it has become more urgent because we're getting better and better at describing the physical basis of cognition and perception, and the gap between the physical description and the felt reality of experience seems, if anything, to be growing rather than closing. There are several major approaches to the hard problem. The most common scientific view is some form of physicalism. Consciousness arises from physical processes in the brain, and in principle it is explicable in physical terms, even if we don't yet know how. Most neuroscientists hold something like this view, but they differ enormously on the specifics. Some, like Daniel Dennett, argue that consciousness is not as mysterious as it seems, that the hard problem is in some sense an illusion generated by the peculiarities of introspection. Others, like Christoph Koch, who has worked with Francis Crick on the neural correlates of consciousness, take the hard problem seriously and believe it points to something genuinely novel in our understanding of the brain. Then there's panpsychism, the view that consciousness, or something like it, is a fundamental feature of the universe, present at all levels of physical reality. Not that rocks are conscious in the way we are, but that there is some proto-conscious aspect to the most basic physical constituents of matter, and that what we call consciousness is what these basic aspects feel like when organized in complex systems like brains. Panpsychism has a long philosophical history, but it has recently attracted the attention of serious philosophers and even some physicists. Integrated information theory, developed by neuroscientist Giulio Tononi, provides a mathematical framework in which consciousness is associated with a quantity called phi, measuring the integrated information in a system. By this theory, any system with non-zero phi has some degree of consciousness. This is a panpsychist-leaning view, and it is taken seriously enough to have been the subject of a major adversarial collaboration between neuroscientists seeking to test it against alternative theories. The physicist Roger Penrose has proposed, working with anesthesiologist Stuart Hameroff, that consciousness is related to quantum processes inside neurons, specifically quantum gravity effects in microtubules, protein structures inside neurons. In this view, the orchestrated objective reduction theory, or orchestroar consciousness, is not just a complex computation but involves quantum-level processes that are not captured by ordinary computational models, connecting consciousness to the deepest levels of physics. Most neuroscientists and physicists are skeptical of orchestroar, finding it overly speculative and poorly supported by evidence. But Penrose's insight that consciousness might require something beyond classical computation is taken seriously by a minority of researchers. And then there's the possibility that is most disturbing of all, that we don't know. That the hard problem of consciousness is genuinely hard. Not just practically, not just because we lack data, but deeply, philosophically hard in a way that might resist any explanation couched in purely physical terms. That there might be an irreducible gap between the description of physical processes and the reality of subjective experience. That the universe might contain, as a fundamental feature, not just matter and energy in space and time, but also experience, the interior, first-person reality of what it's like to be something. And if that's true, then the most disturbing mystery of the cosmos might not be out there at all. It might be right here. inside you. The mystery of why you are experiencing the story, rather than simply processing it in the dark. Now I want to tell you about something vast and ancient that we didn't know existed until very recently. Something that rewrote the map of the universe. It's called the Hercules Corona Borealis Great Wall, and it is the largest known structure in the observable universe. To understand it, you need to know that astronomers study the distribution of gamma-ray bursts, the most energetic explosions in the universe, brief flashes of gamma-ray energy that can be detected from across the observable universe. Gamma-ray bursts are distributed throughout the cosmos, and because they're so energetic, they can be seen at enormous distances. By mapping the positions of gamma-ray bursts at similar distances, similar redshifts, astronomers can probe the large-scale structure of the universe at the very largest scales. In 2013, astronomer Istvan Horvath and colleagues published a paper reporting a remarkable clustering of gamma-ray bursts in a region of the sky centered on the constellations Hercules and Corona Borealis. The clustering suggested a filamentary structure, a concentration of matter, at a redshift corresponding to a distance of approximately 10 billion light-years. The estimated size of the structure, roughly 10 billion light-years across. 10 billion light-years. The observable universe is 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall would be approximately 1/10 the size of the entire observable universe. It is so large that it challenges the cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales. Structures of this scale should not exist if the cosmological principle holds. The universe should be smooth at scales larger than a few hundred million light-years. And yet here, apparently, is a structure 10 billion light-years across. The Hercules Corona Borealis Great Wall is not as well established as some other large structures. It was identified in a relatively small sample of gamma-ray bursts, and the statistical significance of the clustering has been debated. Further studies are needed. But if it is confirmed, it would be one of the most significant challenges to the standard cosmological model since the discovery of the accelerating expansion of the universe. It would mean that the universe is not uniform on the largest scales, that there are structures so enormous that our physical models, our best current understanding of how the cosmos evolved, cannot easily explain them. That whatever process assembled matter in the early universe created concentrations more extreme than our theory predicts. Or it would mean that the cosmological principle is wrong, that the universe is not the same in all directions, that there are preferred directions, preferred scales, preferred structures embedded in the fabric of the cosmos at the very largest levels. And if the cosmological principle fails, much of our cosmological model, which rests on that assumption, would need to be rebuilt. I want to talk now about neutron stars, because they are, pound for pound, the most extreme objects in the known universe that are not black holes, and the stories they tell are among the most violent and strange in all of astrophysics. When a massive star, between about 8 and 20 times the mass of the Sun, runs out of fuel and its core collapses, it doesn't always form a black hole. If the core mass is in the right range, the collapse is halted by a different quantum effect. Neutron degeneracy pressure, the resistance of neutrons to being compressed into the same quantum state. What remains is a neutron star, a city-sized ball of matter with a mass between roughly 1.5 to 2 times the mass of the Sun, squeezed into a sphere approximately 20 kilometers in diameter. Let me give you some numbers, because the numbers for neutron stars are among the most extreme in nature. A teaspoon of neutron star material would weigh approximately 10 million tons, roughly the weight of a mountain. The density of a neutron star is similar to atomic nucleus density, the point at which atomic nuclei touch each other, with all the empty space between atoms eliminated. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's surface gravity. If you could somehow stand on the surface of a neutron star, and of course you would be instantly flattened to a layer a few atoms thick, you would need to exert a force greater than the entire combined output of all nuclear power plants on Earth every second just to lift your hand. The magnetic fields of some neutron stars, called magnetars, are so strong that they dwarf anything else in the universe. The strongest magnetars have magnetic fields on the order of 10 to the 15 Gauss, quadrillions of Gauss, compared to the Earth's magnetic field of about half a Gauss and the strongest magnets we've made in laboratories of a few 100,000 Gauss. At a distance of 500,000 kilometers, roughly the distance from Earth to the Moon is about 384,000 kilometers, so we're talking about slightly farther than the Moon. The magnetic field of a magnetar would be strong enough to disrupt the electron structure of your atoms, pulling the electrons out of their orbitals and rendering chemistry, and therefore biology, impossible. On December 27, 2004, a magnetar called SGR 1806-20, approximately 50,000 light-years away in the Milky Way, released a burst of energy in a matter of about a tenth of a second that was equivalent to the total energy output of the Sun over approximately 250,000 years. This is called a soft gamma repeater giant flare. The burst traveled 50,000 light-years and still hit Earth's upper atmosphere hard enough to ionize it visibly, to compress and disturb the ionosphere, the layer of charged particles surrounding Earth. If SGR 1806-20 had been 10 light-years away rather than 50,000, within a range of nearby stars, the burst would have been powerful enough to cause mass extinction on Earth. There was a magnetar within the Milky Way pointing in our direction that day, releasing the most powerful energetic event ever measured from outside our solar system. And most people on Earth were completely unaware that it happened. Let me talk about time. Because in a documentary about the disturbing mysteries of the cosmos, it would be a profound omission to skip over the fact that time, the most intimate and personal dimension of our existence, the thread on which every moment of every life is strung, is deeply, fundamentally mysterious. We experience time as flowing. We move from the past to the future, one moment after another. The past seems fixed and unalterable, the future open and uncertain. This is so basic to our experience that it's hard to imagine experiencing existence any other way. But here's what physics says about time. In the equations of general relativity and in quantum mechanics, time does not flow. The equations are, for the most part, time-symmetric. They work equally well run forward and run backward. There is no preferred direction of time built into the fundamental laws. Past and future are, in the deepest mathematical sense, on equal footing. The equations describe a static four-dimensional spacetime, sometimes called a block universe, or the eternalist view, in which all moments exist equally, and the distinction between past, present, and future is a feature of our perspective, not of reality. The physicist Brian Greene explores this in his book, The Fabric of the Cosmos, and describes the block universe in stark terms. If this view is correct, everything that has ever happened or will ever happen exists simultaneously in the four-dimensional space-time continuum. Your birth, your life, this moment of listening, every moment yet to come, all of it exists, already, as a fixed structure in the four-dimensional block of space-time. The experience of time flowing is, in this view, a feature of the conscious observer moving along their world line through the block, not a feature of time itself. So why do we experience time as flowing in a particular direction? Why does time seem to have an arrow? Here the answer, fascinatingly, comes not from the fundamental laws of physics but from thermodynamics, from entropy. The second law of thermodynamics says that entropy, roughly, disorder, or the number of possible arrangements of a system, tends to increase over time. An egg can be scrambled but not unscrambled. A drop of ink can diffuse through water but doesn't spontaneously concentrate. Broken vases don't reassemble. And the direction of increasing entropy is what defines the arrow of time in our experience. But this just pushes the mystery back. Why was entropy so low at the beginning of the universe? Why did the universe start in an extremely ordered low-entropy state? A state that allowed entropy to increase over time, and therefore allowed time's arrow to point in a specific direction? We don't know. It's one of the deepest puzzles in physics, sitting at the intersection of thermodynamics, cosmology, and the foundations of time. Some physicists, most notably Sean Carroll, have proposed that the low entropy of the early universe is related to the nature of the Big Bang itself, perhaps to the way the universe emerged from a quantum fluctuation in a larger multiverse, or from some process that naturally produces low entropy initial conditions as a rare but inevitable fluctuation. The details are speculative and contested. But what is not contested is that time, the dimension through which you are living your entire life, is not what it seems. It may not flow. It may be symmetric at the fundamental level. And the reason it seems to point in a direction may have more to do with the statistical mechanics of entropy than with any fundamental feature of reality. There's one more disturbing thing about time, and then I'll move on. The theory of special relativity tells us that time passes at different rates for observers in different states of motion. This is not a metaphor. It's a physical fact with practical consequences. GPS satellites have to account for relativistic time dilation in their calculations, or they would accumulate errors of several kilometers per day. The faster you move relative to a reference frame, the slower time passes for you from that frame's perspective. At the speed of light, time would stop entirely. For a photon, a particle of light, there is no duration. The moment of emission and the moment of absorption are, for the photon, the same moment. It takes no time to travel any distance. And gravity dilates time as well. Clocks run slower in stronger gravitational fields. A clock on Earth's surface ticks slightly slower than a clock at the altitude of a GPS satellite. A clock near a black hole would tick almost infinitely slowly compared to a clock far away. An observer hovering just outside the event horizon of a black hole would, from the perspective of a distant observer, appear to be moving through time so slowly as to be essentially frozen. They would appear to drift toward the horizon for an eternity, never quite crossing it from the outside perspective. But from the infalling observer's perspective, they would cross the horizon in a finite time and continue into the black hole, where time and the causal structure of space-time would become fundamentally different. What happens inside a black hole is not only unknown, it may be unknowable, in the sense that any observer who goes in to find out cannot get the answer back out to tell us. The inside of a black hole is permanently hidden from our universe. It is, in the most literal sense, beyond the horizon of what we can ever know. I want to visit a mystery that is, perhaps, the most personal of all. The mystery that keeps many cosmologists quietly, privately, deeply unsettled. Not because it's the most technically challenging, but because of what it implies about our place in the universe. It's called the fine-tuning problem, and it goes like this. The universe is governed by a set of physical constants, numbers that appear in the equations of physics and cannot currently be derived from any deeper theory. Things like the mass of the electron, the strength of the electromagnetic force, the ratio of the electromagnetic force to the gravitational force, the cosmological constant, the mass of the quarks, the strength of the strong nuclear force. These are just what they are. We can measure them with extraordinary precision. We cannot currently explain why they have the values they have. Now, here's what's startling. When physicists examine these constants and ask what the universe would look like if they were different, even slightly different, they find that almost any change leads to a universe that is radically inhospitable to life, and indeed to complex structure of any kind. Consider the cosmological constant, the one associated with dark energy. If it were much larger than it is, the universe would have expanded so rapidly after the Big Bang that matter would have been dispersed before it could ever have formed galaxies, stars, or planets. The universe would be a thin, featureless gas, cooling forever in an empty space. There would be no complexity, no chemistry, no life. If it were much more negative than it is, if dark energy were a contracting force rather than an expanding one, the universe would have collapsed back on itself almost immediately after the Big Bang, before anything interesting could form. The observed value of the cosmological constant sits in an extraordinarily narrow window, often estimated at roughly 1 part in 10 to the 120, that permits the existence of complex structure. Consider the strong nuclear force, which holds the nuclei of atoms together. If it were a few percent stronger, protons would fuse with each other so readily that almost all the hydrogen in the early universe would have been converted to helium and heavier elements in the first few minutes, leaving no hydrogen to fuel the long-lived, stable stars like our sun that make planetary life possible. If it were a few percent weaker, no complex nuclei could form at all. The universe would contain only hydrogen, and chemistry would be limited to a single element. Consider the ratio of the electromagnetic force to the gravitational force, a ratio of approximately 10 to the 36, meaning electromagnetism is 10 to the 36 times stronger than gravity. If this ratio were significantly different, stars would either burn out too quickly for life to develop, or they wouldn't form at all. The physicist Fred Hoyle, who made an extraordinary prediction about nuclear physics that was later verified, specifically predicting the existence of a resonant state in carbon-12 that was necessary for carbon to be synthesized in stars, was so struck by what he called the fine-tuning of the universe for the existence of life that he wrote in 1981. A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics, as well as chemistry and biology, and that there are no blind forces worth speaking about in nature. Hoyle was not a religious man. He was one of the most creative and iconoclastic scientists of his generation, and the fine-tuning troubled him deeply. Now, I want to be extremely careful here, because the fine-tuning problem is often used to argue for the existence of a designer, a god or some form of cosmic intelligence that set the constants. This is not a scientific conclusion. It's a philosophical one, and there are serious, naturalistic responses to the fine-tuning problem. The most prominent is the anthropic argument combined with a multiverse. If there are an enormous number of universes, each with different values of the physical constants, as eternal inflation suggests, then the fact that we find ourselves in a universe hospitable to life is not surprising. We couldn't possibly be in an inhospitable one. Our very existence selects for a hospitable universe. Among the vast ensemble of universes with all possible values of all constants, we necessarily find ourselves in one where the constants permit us to exist. This is the anthropic principle, and it's a legitimate response to the fine-tuning problem, though it's also unsatisfying to many physicists because it doesn't explain anything. It merely notes a selection effect. Others argue that fine-tuning is less severe than it appears, that if you change the value of one constant, you have to change others consistently, and there may be more combinations that permit complexity than the naive analysis suggests. And others argue that there might be a theory of everything, a deeper theoretical framework unifying all the forces and particles that fixes the values of all constants uniquely. In this view, the constants aren't arbitrary. They're determined by the deeper structure of reality, and when we find that theory, we'll understand why they had to be what they are. String theory was once hoped to be this framework, a theory capable of uniquely determining the laws of nature from first principles. Instead, string theory has produced what is called the landscape, an estimated 10 to the 500 possible configurations of the theory, each corresponding to a universe with different physical laws. Rather than uniquely predicting our universe, string theory seems to encompass almost every conceivable universe, which is simultaneously its greatest apparent strength and its greatest theoretical weakness. Ask yourself this. Does it unsettle you that the universe seems to be precisely, almost impossibly calibrated for the existence of beings like you? Does it feel like evidence of something? Or does it feel like the inevitable result of being the kind of creature that can notice? And what does the answer you feel most naturally reach for say about you? There's a discovery from 2017 that I want to describe in some detail, because it was genuinely historic, because it was a moment of pure scientific joy and wonder, and because it opens a door onto one of the most extreme and violent phenomena in the universe. On August 17, 2017, a signal arrived at the LIGO and Virgo gravitational wave detectors. It was a chirp, a rising tone of gravitational waves that lasted approximately 100 seconds, far longer than the brief, sharp chirps of merging black holes detected earlier. Almost simultaneously, a gamma-ray burst was detected by the Fermi and Integral space telescopes. A short gamma-ray burst, lasting less than 2 seconds, arriving from the same direction as the gravitational wave source, approximately 1.7 seconds after the merger. And then optical telescopes around the world, alerted by a real-time alert system that allowed them to slew their telescopes to the source within minutes, began detecting the aftermath of the event in a galaxy called NGC 4993, about 130 million light-years away. What astronomers had detected, for the first time in history, was the collision of two neutron stars. And in doing so, they confirmed, directly, one of the most important predictions about the origin of heavy elements in the universe. When two neutron stars spiral together and merge, the collision produces conditions of extreme density and neutron flux. The collision is like squeezing a billion nuclear reactors worth of material together in a millisecond. These conditions are exactly what is needed for the rapid neutron capture process, the R process, by which atomic nuclei rapidly absorb neutrons to build up the heaviest elements in the periodic table. Elements like gold, platinum, silver, uranium, all the heavy elements that natural radioactive processes cannot create in the interior of stars. The light from the neutron star merger, a kilonova, created by the radioactive decay of freshly synthesized heavy elements, was observed across the electromagnetic spectrum. The spectral features showed the unmistakable signatures of strontium and other heavy elements. The color evolution of the kilonova was consistent with large amounts of gold and platinum being synthesized in the event. Roughly 10 times the mass of the Earth in gold, and similar quantities of platinum, created in a single cosmic explosion. Every piece of gold on Earth, every ring, every coin, every circuit board, was forged in the collision of neutron stars billions of years ago, scattered through the galaxy, and incorporated into the cloud of gas and dust that eventually became our solar system. Gold is literally the remnant of catastrophic cosmic violence, so ancient and so remote that it predates the Earth itself. Think about that the next time you hold a gold ring. What you're holding is the ashes of a neutron star collision, the debris of the most violent event in the universe, forged in temperatures and densities beyond anything we can reproduce in a laboratory, scattered across space for billions of years before becoming part of your world. There are things in the universe that challenge even the concept of strange. Let me tell you about some of them. Quasars. In the late 1950s and early 1960s, radio astronomers began detecting compact radio sources in the sky. When optical astronomers identified the objects responsible and took their spectra, the fingerprint of light that reveals an object's composition and motion, they found something baffling. The spectral lines were shifted to the red by enormous amounts, indicating that the sources were moving away from us at a substantial fraction of the speed of light, which meant they were enormously distant. And yet they were bright. Impossibly bright. If they were as far away as their redshift suggested, and yet as bright as they appeared, they must be producing more energy than entire galaxies. Far more, from a region that appeared, in early observations, to be almost point-like. These objects were called quasi-stellar objects, quasars, and what they turned out to be was supermassive black holes, millions to billions of times the mass of the Sun, actively consuming matter from a surrounding accretion disk and converting it to energy with terrifying efficiency. The most luminous quasars outshine their entire host galaxies by factors of hundreds. Some quasars are so luminous that they are visible across the entire observable universe. We have detected quasars at redshifts corresponding to times when the universe was less than 1 billion years old, quasars hosting black holes of billions of solar masses that shouldn't, according to our models, have had time to grow so large so quickly. The existence of these ultramassive quasars in the early universe is one of the most actively debated problems in astrophysics. How do you grow a black hole of 1 billion solar masses in less than 1 billion years? Even if you start with a massive seed, a black hole of thousands or tens of thousands of solar masses, perhaps from the direct collapse of an enormous primordial gas cloud, it seems almost impossible to grow to billions of solar masses that quickly by conventional accretion. Some researchers have proposed super-Eddington accretion at rates exceeding the theoretical limit set by radiation pressure, as a solution. Others have proposed exotic seed mechanisms. The problem is not resolved. Then there are pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles, sweeping around like cosmic lighthouses. Because a neutron star is so compact and so massive, it can rotate with extraordinary speed without flying apart. Some pulsars, called millisecond pulsars, rotate hundreds of times per second. The fastest known pulsar, PSR J1748-2446 AD, rotates 716 times per second. A neutron star, 20 kilometers across, containing roughly twice the mass of the Sun, spinning more than 700 times per second. The equatorial surface of this star is moving at approximately 1/4 the speed of light. Pulsars are among the most precise natural clocks in the universe. They tick with a regularity that rivals atomic clocks. This precision has made them extraordinarily useful scientific instruments. The timing of pulsars has been used to indirectly confirm the existence of gravitational waves before LIGO, to search for low-frequency gravitational waves generated by supermassive black hole binaries, and potentially to detect ultra-precise variations in the fabric of space-time. Now let me tell you about the most dangerous place in the local universe. Not far off, not in another galaxy. Dangerously close, cosmically speaking. And it's called the Great Attractor. In the 1970s and 1980s, astronomers mapping the motions of galaxies noticed something anomalous. Our galaxy, the Milky Way, along with our local group of galaxies, and the larger Virgo supercluster of which we are part, is not moving in a random direction. It is moving. It is being pulled, accelerated, toward a specific region of the sky in the direction of the constellation Centaurus, at a speed of approximately 600 kilometers per second. Everything in our cosmic neighborhood is falling toward something. Something massive. Something we couldn't see because it lay behind the zone of avoidance. The region of the sky obscured by the plane of our own Milky Way galaxy, where dust and gas block our view of what lies behind. Astronomers called the invisible attractor the Great Attractor. In the 1990s, as X-ray and radio observations began to penetrate the zone of avoidance, the Great Attractor was revealed to be centered on a massive galaxy cluster called the Norma Cluster, sitting at the heart of a supercluster known as the Hydra-Centaurus supercluster, approximately 150 to 250 million light-years away. But it didn't end there. In 2008, astronomers using X-ray data from hundreds of galaxy clusters found that the drift wasn't explained by the Great Attractor alone. There was a broader, larger-scale motion, a dark flow, involving clusters across a much larger volume, several hundred million light-years. The source of this dark flow appeared to lie much farther away, beyond the observable universe, in some cases, or at the very edge of it. Some researchers propose that there might be a vast, ultramassive concentration of matter beyond our cosmic horizon. Something so massive that its gravitational influence can be felt across billions of light-years, pulling not just our neighborhood but a large fraction of the observable universe in a preferred direction. This is highly controversial. The dark flow findings have not been universally accepted. Subsequent analyses of the CMB data have not confirmed the signal for all researchers. But it remains a possibility taken seriously enough to be the subject of ongoing research. And if it is real, if there is something beyond the horizon of our observable universe massive enough to tug hundreds of millions of galaxies across billions of light-years, then we are being pulled toward something we cannot see, something outside our universe, something utterly beyond our reach. Let me now talk about something that happened in the early universe, specifically, something that almost certainly should not have left us here at all. When the Big Bang occurred, it produced matter and antimatter in roughly equal amounts. This is what our best theories of particle physics predict, and there's no obvious reason within those theories why the two should be produced in anything other than a near-perfect 1-to-1 ratio. Matter and antimatter are mirror images of each other. Same masses, but opposite electric charges and other quantum numbers. When they meet, they annihilate each other in a burst of pure energy. If the early universe produced equal amounts of matter and antimatter, then as the universe cooled and particles formed, matter and antimatter should have found each other and annihilated in pairs. The universe should have been left with nothing but a sea of photons, pure light, with no leftover matter to form atoms, stars, galaxies, or anything else. No life. No observers. And yet, here we are. The universe is overwhelmingly dominated by matter. Antimatter exists, but in minuscule quantities, produced in high-energy processes like cosmic ray collisions or particle accelerators. The observable universe is full of matter and essentially empty of primordial antimatter. Something, in the first moments after the Big Bang, broke the symmetry between matter and antimatter. For every billion pairs of matter and antimatter particles that annihilated, there was approximately one extra matter particle that survived. 1 in a billion. And that tiny residue, 1 in a billion, is everything. Every star, every galaxy, every atom in every living thing. We do not know what caused this asymmetry. We know it is related to a concept called CP violation, the violation of a symmetry called charge parity that can in principle cause matter and antimatter to behave slightly differently. We know CP violation occurs in the weak nuclear force, and we have measured it in particle decays at the Large Hadron Collider and elsewhere. But the amount of CP violation in the standard model of particle physics is far too small to explain the matter-antimatter asymmetry we observe. There must be additional sources of CP violation beyond what we currently know, new physics, beyond the standard model, that were responsible for the universe's matter asymmetry in its first moments. This is not a minor gap in our knowledge. The existence of everything, including you, required a physics we don't yet understand. You are here because of an asymmetry we cannot fully explain, a tiny imbalance in the very first moment of the universe, without which nothing you've ever known, including the atoms in your body, would exist. There is a concept I need to tell you about that is so strange, so far outside everyday experience, that when physicists encounter it in the equations for the first time, it can produce a reaction very close to existential vertigo. It's called the many worlds interpretation of quantum mechanics. You'll remember we discussed the measurement problem in quantum mechanics. The fact that before a quantum system is observed or interacts with something, it exists in a superposition of all possible states, and the act of measurement appears to collapse the wave function to a single outcome. What causes this collapse? Why do we observe definite outcomes rather than superpositions? The Copenhagen interpretation, the standard textbook answer, says that the wave function collapse is just what happens. There's no deeper mechanism. You just accept that observation produces definite outcomes and don't ask what observation means at a deeper level. The many worlds interpretation, proposed by physicist Hugh Everett III in his 1957 doctoral thesis, takes a completely different approach. Everett said, what if there's no collapse? What if the wave function never collapses, and instead all possible outcomes actually occur? In this interpretation, every time a quantum event with multiple possible outcomes occurs, which is to say, constantly, at every point in space, at every moment, the universe branches into multiple copies, one for each possible outcome. All outcomes occur. In each branch, observers see a different result. The universe is constantly, endlessly splitting into a vast and growing tree of branching realities. This is not a metaphor. In the many worlds interpretation, it's literal. When you toss a quantum coin, when any quantum measurement is made, you don't get heads or tails. You get both. In one branch of the universe, you get heads. In another branch, which is just as real as yours, you get tails. And the you in each branch has no knowledge of the other. The many worlds interpretation is not fringe physics. It is taken seriously by a significant fraction of physicists, perhaps even a majority of those who have thought carefully about the foundations of quantum mechanics. It has the significant theoretical advantage of being completely consistent with the mathematical formalism of quantum mechanics, requiring no additional rules or postulates beyond the Schrödinger equation. It is also, in many ways, the most unsettling interpretation on offer. If many worlds is correct, then there is a version of you, just as real as you, who made every different choice you've ever made. There are versions of you who are living wildly different lives. There are versions of you who are not alive. There are versions of you who were never born. Every quantum event, and quantum events underlie everything, has produced a branching. The tree of reality is incomprehensibly vast, an ever-growing, ever-branching structure of realities, each one as real as yours, each one populated by beings who believe their branch is the only one. The physicist David Deutsch, one of the most vocal advocates of the many worlds interpretation, goes so far as to say that we have experimental evidence for the existence of other worlds. Not direct evidence, but the interference patterns observed in quantum experiments that can, in his view, only be explained if the quantum system is computing with the resources of multiple simultaneous branches. This is controversial and rejected by many physicists, but Deutsch argues it seriously and rigorously. The many-worlds interpretation is not proven. No interpretation of quantum mechanics is proven. The interpretations are, by design, empirically equivalent. They all make the same experimental predictions. The difference is philosophical. What do we believe is really happening? And the many-worlds answer that every possible quantum outcome happens, and the universe branches endlessly, is a picture of reality so vast and so strange that it makes the concept of the universe seem almost quaint. Let me tell you about one more mystery. Perhaps the quietest mystery. Perhaps the one that requires the least exotic physics and the most honest reckoning with what we are and where we are. Look at the night sky. In every direction you point a sufficiently powerful telescope, you see galaxies. Thousands in a single image. The Hubble Ultra Deep Field image, taken by the Hubble Space Telescope in 2004 by pointing the telescope at a tiny, apparently empty patch of sky and exposing for more than 11 days, revealed approximately 10,000 galaxies, each a collection of hundreds of billions of stars, in a patch of sky smaller than 1/10 the diameter of the full moon. In 2016, a team led by Christopher Consulis of the University of Nottingham estimated, from the Hubble data and models of galaxy formation, that the observable universe contains approximately 2 trillion galaxies, 2,000 billion galaxies, each with hundreds of billions of stars, most of those stars with planets. 2 trillion galaxies. The total number of stars in the observable universe is estimated at approximately 10 to the 24, a septillion. That is a 1 followed by 24 zeros. And we have been listening for signals from other civilizations for 60 years. We have found, in all that vastness, in all those septillion stars, essentially nothing. The wow signal, once unrepeated. A few other anomalies, all with plausible natural explanations. It could be that life is rare. It could be that intelligence is rarer still. It could be that civilizations are brief. It could be that everyone is hiding. It could be that interstellar communication is harder than we think. It could be that the signals are there, but we're looking in the wrong way. Or it could be something far simpler and far more devastating. That in a universe of 2 trillion galaxies, we got lucky. That the specific, improbable chain of events that led to complex life here, the right star, the right planet, the right chemistry, the right impacts, the right catastrophes, the right amount of time, happens almost nowhere else. And that what this means is not that we are special in a comforting sense, but that we are special in a lonely sense. That the universe is full of fire and light and drama and transformation, and of all the things it has produced in 13.8 billion years of existence, minds capable of looking at it and asking why might be the rarest thing of all. And if that's true, if conscious observers are so rare that we may be the only ones in our observable universe, then what we do here, on this small world, in this brief time, carries a weight that's almost impossible to articulate. Not because someone is watching, but because no one is. Because the universe is not watching itself. We are its eyes. We are the mechanism by which the cosmos became aware of itself. Physicist Neil deGrasse Tyson has said, "We are part of this universe. We are in this universe, but perhaps more important than both of those facts is that the universe is in us." Every atom in your body was forged in a star. Every atom was scattered into space by a stellar death. The iron in your blood was made in a supernova. The calcium in your bones was made in a dying star. The oxygen you are breathing was manufactured by fusion in stellar cores billions of years before the Earth formed. You are the universe experiencing itself. Carl Sagan said it more simply, and perhaps more beautifully. We are a way for the cosmos to know itself. But let me not end on a note of comfortable wonder. Because we set out to talk about disturbing mysteries, and the most disturbing mystery of all might be this: we don't know how long we have. Not as individuals. Of course not. but as a civilization, as a species, as the only known mind in the cosmos. The sun will continue to shine for approximately 5 billion more years. After that, it will expand into a red giant, most likely engulfing Mercury and Venus and scorching the Earth beyond any possible habitability. Eventually, it will shed its outer layers and leave behind a white dwarf, a glowing ember of carbon and oxygen that will slowly cool over trillions of years. The Earth, if it survives the red giant phase, will be a frozen, airless rock orbiting a cooling cinder.